So, hello everyone again. This is your lecture 5 part 3 of semiconductor electronics, materials, devices and simple circuits. In this we will start with a new subtopic, that is application of your diodes as a rectifier. Okay. So, before going into that topic, let us first revise every concept which we studied till now, the basic concepts which are required in the further application part. Okay. So, I am Sameer Lavankar. Let us begin our discussion. So, right now we will be starting with the application of the junction diode as a rectifier. Before going into this, let us first revise every concept, basic concept which are being required forward, and then we can move. Okay. So, first of all, in the extrinsic semiconductor concept, so in the extrinsic semiconductor concept, what we understood was there are two types of semiconductor. One is your N type, another is your P type. Okay. What happens in an N type? Pentavalent impurity is being added up. What happens in a P type? Trivalent impurity is being added up. Okay, so a pentavalent impurity is being added up here and a trivalent impurity has been added up here. Fine. After this, second thing which we can understand is that electrons are the majority charge carriers, and in P type holes are the majority charge carriers. Similarly, holes are the minority charge carriers here, and electrons are your minority charge carriers here. Okay, so that is all main concept which we require from the extrinsic semiconductor. Moving on to the p-n junction diode. So, what we understood in p-n junction diode? So, in p-n junction what we understood is, so let us suppose this is the p-n junction being made. So, this is basically your p, this is basically your n, and here you can find out a depletion region being formed. Okay. So, diffusion current is being formed in this direction here. So, this is your diffusion of electrons, this is your diffusion of holes, then next thing is this is your drift current, and here this is your drift current. Okay. So, drift current basically depends upon the this is here drift current would be for holes and here drift current will be for electrons. Okay. So, that is how this thing is being taking place, and next thing was about p-n junction is completed. The next thing was your semiconductors. So, in semiconductor diode what we understood is in semiconductor diode we understood two different concepts. First was forward biasing, second was reverse biasing. Okay. Next thing which we understood was in forward biasing the amount of current which is generally being measured is in milliamperes. The current which is measured in reverse biasing is generally in microamperes. Okay. Then we also understood the VI characteristics. Okay. So, this was voltage, this was current, this was in milliamperes, this was in microamperes, and this was also voltage. So, these were something of the order of 20, 40, 60, 80 etc., and these were very small, let us say 0.2, 0.4, 0.6, 0.8. Okay. So, it was something in this direction, and this was something in this direction. Okay. So, that is how the VI characteristic was made. Okay. Fine. That being said, I think that this is the main information, that this is a simple small revision before starting the application part of the junction diodes. Okay. So, now that being said, let us start with the 7th subtopic, that is application of junction diode as a rectifier. Okay. So, now let us understand what is this being talked about here. So, what is the basic concept which we are trying to implement here. Okay. See, so from the Vi characteristic of a junction diode, we see that it allows the current to pass only when it is forward biased. Okay. So, just let me explain to you from here. Okay. So, as you can see here, that the current is generally being passed when only and only it is in forward biased. Okay. So, in general terms, even in reverse bias, we do not take into this into scenario, we only take it only up to reverse saturation current. Okay. So, only till this part, therefore, what we say that generally there is no current being generated, or the current is very small in the reverse bias, and only the current which is being usable or being used is only for forward biasing. So, that is the current which is being used. Okay. Fine. So, if an alternating voltage is applied across a diode, so let us say if I apply alternating voltage. So, this is an example of an alternating voltage. Okay. So, what does an alternating voltage do? It goes in plus V once, it goes in minus V next time. Okay. So, therefore, if an alternating voltage is applied across a diode, the current flows only in that part of the cycle when the diode is forward biased. Please try to understand this situation very carefully. Okay. So, what happens actually is, I will try to make you understand again. So, there is something called as forward biasing, there is something called as reverse biasing. Fine. Now, in general terms, what we can say that the current passing here can be approximated to be 0. Fine. Here the current can be said to be current I. So, that is some amount of current is being produced here. Okay. Now, what was the basic definition of forward biasing? The forward biasing definition states that when the battery potential is such that the positive terminal of the battery is connected to the p type, and similarly negative terminal is connected to the n type, then that is called as forward biasing. The reverse is true for reverse biasing, that is the positive terminal of the battery is connected to an n type and the negative terminal is connected to a p type. Okay. So, what is generally happening? Either we can change the semiconductor diode, or what we can say, we can change the battery, correct. So, what is basically happening, if the battery is providing a potential of V in one sense, so what we can say, it is providing a minus V in another sense. What does it mean? That let us say if we apply a alternating voltage, then at one time in the first cycle, in first half cycle, it can be said as forward biasing because a plus V is being applied there. In the second time, it can be said that we are doing a reverse biasing because minus V is applied there. So, that is how what we can say, that when the input is like this, then for every reverse biasing which is happening, we will not get a output. Why we will not get a output? Because at that locations it is under reverse biasing, and in reverse biasing the current is approximated to be equal to 0. Okay. So, that is how this diagram is being made here, and hence how we can use the junction diode as a rectifier. So, basically we are rectifying the image. So, basically inside we put it as a alternating source, and output it comes out to be like this. Okay. So, that is how we use a semiconductor diode as a rectifier. So, this property is used to rectify alternating voltages, and the circuit used in this purpose is called as a rectifier. Okay. So, the circuit which is used in this purpose is called as a rectifier. Fine. Now, if an alternating voltage is applied across a diode in series with a load. Okay. So, let us say we apply this alternating voltage across a diode in series with a load. So, let us say this is the diode being applied and this is the load being applied. Okay. Then a pulsating voltage will appear across the load only during the half cycles of the AC input, during which the diode is forward biased. Quite clear. So, in the first cycle the current will be passing through it, and therefore, a voltage would be appearing across the resistor. If there is no current, there is no voltage being applied here, because we know what is basically V. V is nothing but equal to IR, correct. If I is present, then IR will be valid. If I is 0, then voltage will also be equal to 0, correct. So, that thing can be produced. So, when we try to find out the voltage between this RL, we can understand that at which part of the cycle it is forward biased and at which part of the cycle it is reverse biased. Okay. Fine. So, if an alternating voltage is applied across a diode in series with the load, it is, as you can see clearly, that it is in series with the load, a pulsating voltage will appear across the load. Okay. So, a pulsating voltage will appear across the load. Pulsating, what does it mean of pulsating? So, it appears at a pulse. Okay. So, a pulse is being observed for the first cycle, then there is nothing there, then again something is observed, then there is nothing there. So, it can be observed as a pulse. Okay. So, that is what is saying as a pulsating voltage. Okay. So, a pulsating voltage will appear across the load only during the half cycles of the AC input, during which the diode is forward biased. Okay. So, it is only and only possible or only and only visible when the diode is forward biased. Okay. Such rectifier circuit as shown in figure is called as the half wave rectifier. Okay. So, you can understand clearly why it is called as half wave rectifier, because only half wave is propagated, only half wave is rectified. A question may arise. So, there can there be a situation in which full wave can be rectified? So, yes, there is a situation in which full wave can be rectified, which we will understand in subsequent slides in this chapter only. Okay. Okay. So, let us now keep our discussion to half wave rectifier only. So, such rectifier circuit as shown in the figure is called as the half wave rectifier. Okay. So, this is basically the circuit for half wave rectifier. Okay. Now, the secondary of a transformer supplies the desired AC voltage across terminals A and B. Okay. So, if you remember correctly the concept of transformer, so there is something called as primary side, there is something called as secondary side. Okay. So, this secondary side, so this is basically a solenoid here. Okay. So, now due to this solenoid, the current or the voltage is being transferred from this location to this location. Okay. And hence, the voltage is being supplied, the desired AC voltage is being supplied to the secondary part, and hence there is a movement here. So, that is how the input AC voltage is being obtained here. Okay. So, the secondary of a transformer supplies the desired AC voltage across terminals A and B. Now, when the voltage at A is positive, let us say the voltage here is positive. Okay. The diode is forward biased and it conducts. So, when it conducts, it is the same. Okay. When A is negative, means when we are talking about this location here, the diode is reverse biased and it does not conduct. So, there is nothing observed here. The reverse saturation current of a diode is negligible. Please remember that in general terms what we say, that this reverse saturation current, what is reverse saturation current? The current which is obtained in a reverse biased semiconductor diode is called as your reverse saturation current. Okay. So, the reverse saturation current of a diode is negligible and can be considered equal to 0 for practical purposes. Okay. So, practical purposes we consider it to be 0. The reverse breakdown voltage of a diode must be sufficiently higher than the peak AC voltage at the secondary of the transformer to protect the diode from reverse breakdown. So, they are just saying that this voltage which is being observed here should be greater than VBR, so that there is not enough amount, so that it can also work in reverse bias, and if it works in reverse bias, basically the PN junction diode will get destroyed due to overheating. Okay. So, we just need to make sure that the voltage supplied by the secondary of the transformer should not be greater than the breakdown voltage. Okay. So, that is only being written here, that the reverse breakdown voltage of the diode must be sufficiently higher. Okay. This is basically VBR is talked about here, that it should be sufficiently higher than the peak AC voltage. What is the peak AC voltage? The peak AC voltage would be this value, correct, the peak of this AC voltage. So, this will be the peak voltage here, higher than the peak AC voltage at the secondary of the transformer to protect the diode from reverse breakdown. Okay, to protect the diode from the reverse breakdown. So, that is the thing which I explained to you. Fine. So, therefore, in the positive half cycle of AC, there is a current through the load resistor RL. Okay. So, in this positive half, there is a load, or basically there is a current through the load resistor RL, and we get an output voltage which is shown in this figure B. So, you can see that this is the output voltage which is being observed, whereas there is no current in the negative half cycle. So, in this half cycles there is no current being observed here. So, there is nothing observed here. Okay. In the next positive half cycle, again we get the output voltage. So, again we get the output voltage like this, and again because there is a forward reverse biasing happening in this location, then again we will not get anything. Okay. So, in the next positive half cycle again we get the output voltage. Thus, the output voltage, though still varying, is restricted only to one direction and is said to be rectified. So, that is why we say that the voltage is being rectified. Since the rectified output of the circuit is only for half of the input AC wave, it is called as half wave rectifier. So, I think till this time you have understood why it is called as your half wave rectifier. Okay. Now, let us understand the full wave rectifier. So, what would be happening in full wave rectifier? Here the complete wave would be captured by the circuit on the right hand side. How we will capture it? So, there will be some transformation happening in the circuit, and then we can understand the full wave rectifier also. Okay. So, the circuit using two diodes, one diode, second diode. So, the circuit using two diodes shown in figure A gives output rectified voltage corresponding to both the positive also, the negative also. Okay, as well as negative half of the AC cycle. Hence, it is known as the full wave rectifier. Okay. How is the output being obtained? We will try to understand this. First, let us keep on it, and let me keep on iterating, and then we can understand. So, hence it is known as your full wave rectifier. Here, the P side of the two diodes are connected to the ends of the secondary of the transformer. Okay. So, what we did, the P side, this was basically your P side. So, this P side is connected to the central, is connected to the secondary of the transformer. Okay. So, this is the secondary of transformer, and we connected these both of these P side of the diodes. So, that was the first assembly expression here, that first of all we connected the P side of the two diodes to the ends of the secondary of the transformer. Okay, fine. Next thing is the N side of the diodes are connected together. As you can see, the N side of these are connected together, quite evident, and the output is taken between this common point of the diodes and the midpoint of the secondary of the transformer. Okay. So, now what where do we take the output? So, this is one of the output here taken, and this is one of the output here taken. So, these are the locations at which the output is being taken. Fine. So, this thing is also explained. Next thing is, so for a full wave rectifier, the secondary of the transformer is provided with a central tapping, and so it is called a central tap transformer. Okay. So, it is just a type of transformer only, we will not go into much detailing of what is central tap transformer here. So, because there is a central tap here, there may be a usage of the central tap which you will understand, and hence this is called as a central tap transformer. Okay. Fine. So, as can be seen from figure C, so this is how the output of a full wave rectifier will be observed. In the previous half wave rectifier it was something like this time it is something like this. Okay. So, each diode rectifies only for half the cycle, but the two do so for alternate cycle. Okay. So, one time this one rectifies, one time this one rectifies, next time this again rectifies, next time this again rectifies, and the cycle goes on. Okay. Thus, the output between their common terminals and the center tap of the transformer becomes a full wave rectifier output. Okay. Thus, the output between the common terminals, this is the output between the common terminals and the center tap of the transformer, becomes a full wave rectifier output. So, this is basically a full wave rectifier output. Note that there is another circuit of full wave rectifier which does not need a center tap transformer, but needs 4 diodes. Okay. So, they are just telling you an expression here. So, that is not required right now, we are just understanding how can the application be used. So, we are just saying that there may be another circuit which can be used as a full wave rectifier, but not using a center tap transformer, but that will require 4 diodes. So, let us leave that into situation for now. Let us understand first the mechanism of what is happening here for a full wave rectifier. Fine. So, suppose the input voltage to A with respect to the central tap at any instant is positive. Fine. So, let us say that first of all we try to add some voltage to A. and at any instant it is positive. So, it is clear that at any instant the voltage at B is being out of phase and will be negative as shown in the figure B. Okay. So, what is being explained here? It is just saying that if a positive voltage is being applied at this location, then at this location it will be negative voltage. So, it will be positive for one sense and it will be negative for one sense. Okay. So, what we can say from this point, that there will be forward biasing for one sense and negative biasing for the another sense. Okay. So, diode D1 get forward biased, this get forward biased and conducts, while D2 being reverse biased does not conduct, so this does not conduct. Hence, during the positive half cycle we get an output current and output voltage across a load resistor as shown in figure C. Okay. So, that is how we can obtain current for the first cycle. Okay. So, let me stop it here only. We will understand the further discussions about this topic in the next part of the lecture. So, then we can understand what happens in the second type. So, basically same thing happens, this time this will become forward biased, this will become reverse biased, but let not be hesitant, we will go slowly and understand the complete mechanism. Okay. So, let me stop it here only. So, the course progress for you. So, we started with the introduction, then we went on to classification of metals, conductors and semiconductors, then intrinsic semiconductor, then an extrinsic semiconductor, then PN junction, then semiconductor diodes, and right now we are on the application part, that is the first application, which is application of junction diode as a rectifier. In this we have completed the half wave rectifier and right now we are on the full wave rectifier. Fine. So, then we can move on to special purposes PN junction diodes, junction transistor, and finally to the topic of digital electronics and logic gates and integrated circuits. Integrated circuit is a very small concept, this may take time, logic gates is a different concept, a new concept for you. So, it will be a long topic. Okay. So, that being said, let us understand this in the next lecture. So, thank you so much.